Good whatever to everyone. Morning, afternoon, night. I don't know when you're watching this. Okay, so in this section is all about trigonometric integrals. So dealing with sine, cosine, secant, tangent, cosecant, cotangent, all of them are fair game. And again, just a reminder, a lot of calculus, a lot of what this is just rewriting things to make sense of it and to actually make these integrals possible. So this is something in your tool bag that is useful. It is something that will be given to you on the AP test if they're going to ask you a question about it. It'll be given like in the problem stem. Quizzes test for me, I'll probably just put it on the first page, and it's up to you to decide when to use it. This is something very well your college professor could expect you to know as well, but these are just called power-reducing identities. So it's a way that we can get sine squared down to a trig function to the first power, or a way that we can get cosine squared down to a trig function with one power. Other than this, we don't really do too much, but let's just roll through these and see when it's going to be useful. Again, it's just another tool. I don't have to use it every time. It's just something that is an option to use. Okay, so in my first one, I have sine to the third dx. I do not know the antiderivative for sine, or sine third, right? Normally, we would have to do u substitution, where I would let u be sine of x, and then du would be cosine of x dx, but I don't have a cosine involved in my integrand. Well, couldn't I create one using the fact that sine squared plus cosine squared equals 1? And what that can allow me to do is if I make this sine times 1 minus cosine squared dx, right? So that's taking one of the sine squareds and changing it into 1 minus cosine squared. Now I have it in a way that I can work with this, because I chose a bad u in the first time I looked at this, but now if I let u be cosine, then du is negative sine, which, hey-oh, I have sine times dx, I have cosine right there, so this can turn into negative the integral of 1 minus u squared du, right? That negative is coming from the negative here. You need to move it over. So then this is negative of u minus u to the third over 3 plus c, and u is cosine, so this is negative cosine of x plus cosine to the third of x over 3 plus c. And that's all it is. All right, so really the whole trick of this was using our Pythagorean identity to rewrite this thing such that we could actually use a u substitution with those two functions. All right. Similar idea. With this one, you can rewrite either of these, right? Because cosine squared of x is 1 minus sine squared. But there are two cosine squareds in that, so like it's cosine squared squared. So instead of rewriting my cosine, right, if I let u be sine, then du would be cosine. So I would need to have some cosines left. But if I rewrite both of those, I won't have any cosines left. So maybe if we think about changing our u, nope, not what I meant to do, to cosine, then du would be negative sine of x dx. So I just need to have one sine in my integrand. Well, I can do that if I change one of the sine squareds. So I'm going to make this sine times 1 minus cosine squared times cosine to the fourth dx. And if I rewrite this, this is sine of x cosine to the fourth minus cosine to the sixth dx. Right, and the reason I did that is just so that I have sine dx kind of out by itself, and I don't have to think about setting up in different integrals or anything like that. So now if I use my u substitution on this step, then I can let u be cosine. Right, so it's going to be negative the integrand of u to the fourth minus u to the sixth du do my antiderivatives. So negative u to the 5th over 5 minus u to the 7th over 7 plus c. 1 minute. Sorry, I had to talk to somebody. So then, right, negative cosine to the 5th of x over 5 minus cosine to the 7th plus cosine to the 7th of x over 7 plus c. And that's all there is to this one here. Okie doke, moving on. So this one, x squared sine squared of x. Well, I can replace sine squared with 1 minus cosine squared, but that doesn't really help me with u substitution or anything. I could try to do my u and dv stuff, where u is what, sine squared of x, and then du would be 2 sine x cosine of x. But then that's just going to create more and more and more terms. Well, what if we use my power reducing? Hey! So sine squared is 1 minus cosine of 2x over 2. So let's make this the integral of x squared, 1 minus cosine of 2x over 2 dx. I'm going to go ahead and factor out the 1/2 and separate the x squared into its own integral. Right, so distributing that will be an x squared minus cosine 2x x squared. Right, so x squared minus x squared cosine 2x. All of it over 2, so over 2 over 2. So I have everything I need. I can do the antiderivative of x squared pretty easily, right? It's just x cubed over 3. So then now I need to think about the second part. Well, I'm going to do integration by parts, and I'm going to do the tabular method. That is a v. So u, I would choose x squared because it eventually goes down to 0. And dv would be cosine of 2x. So let's see, antiderivative. So what, 1/2 sine 2x, negative 1/4 cosine 2x, negative 1/8 sine 2x. That should be, yeah, that's right. And then my alternating signs. So plus, minus, and I'm going to go across and down, cross and down, cross and down. So I have the first part, that's just x cubed over 3. So I have x to the 3rd over 6 minus 1/2 times all of my integration by part stuff. So I have x squared sine of 2x over 2 plus x cosine of 2x over 2, since that will reduce, and minus 2 over 8 is 1/4, so sine of 2x over 4 plus c. All right, and you can distribute that 1/2, but meh, I ain't going to worry about it none. I'm just going to leave it just like that. All right, part D here. So there's a few different ways to do this one. You can actually do it straight away, where say I let most students go here first. Let u be tangent of x over 2. Then du is secant squared of x over 2 times 1/2. So this becomes 2 the integral of u du. So this becomes u squared over 2 times the 2 would just make that u squared plus c. So in this case it is equal to tangent squared of x over 2 plus c. Now if I look at this in a different way, I can do this and come up with an answer that looks different, but is really the same, and I'll show you that it's the same. But I'm just trying to show you guys there's different ways to look at these problems. Because say if I let u be secant of x over 2, then my du is 1/2. The derivative of secant is secant tangent. dx. Missed it up there. Right, so then secant tangent, since I have two secants, one of them is taken up with a u, the other one is taken up with my du. So this still becomes 2 integral of u du. U squared over 2, we'll multiply with the 2 to make that 1. So this becomes u squared plus c, which is secant squared of x over 2 plus c. But those look totally different, right? Well, let me show you. I know I have it somewhere. Right, so on Desmos, oh man, let me type them in real quick. Right, so here's secant squared of x over 2. Here is tangent squared of x over 2. Those are totally different graphs, right? But we have not evaluated what c would be. So really, truly, if I add 1 to this, then hey, it's the same one. So they're just going to be off by some value c. If it was supposed to be secant squared plus 2, then it would be tangent squared plus 3. So you can come out with different functions and still get the same answer, depending on what you make for substitutions and things like that. Alrighty, moving on. So here, the way that I look at these and I try to approach these is, what is my u going to be? Well, if I let my u be tangent, then du would have to be secant squared. So I would need to have 2 secant squares. So if I got rid of 2 of those, I would be missing 1. Well, let's see what happens if I keep this u as secant. Then du would be secant tangent. So that's probably the way that I want to go, because I can get rid of 2 of these tangent and make it just 1 to match with my du. So let's try to go that way. Let's get rid of 2 of those tangents. So this is the integrand of secant to the third, x over 2, tangent of x over 2, and then secant squared minus 1 dx. I'm going to rewrite this and multiply my secants together in there. I'm going to leave one of them out though, so that I have my du as secant tangent, and it's kind of just hanging there. So make sure that you pause the video if you need to and understand where everything is coming from. But this will be secant to the fourth of x over 2 minus secant squared of x over 2 times secant of x over 2 tangent of x over 2 dx. All right, because now if I let my u be secant, then du is secant tangent dx. Right, here's my du, that's why I wrote it like that, so it's all together. And I have my u's, so the integral of u to the fourth, whoop, I missed my 1/2 in my du. 1/2, so this will be 2 u to the fourth minus u to the second du. So I have 2 u to the fifth over 5 minus u to the third over 3 plus c, and u is secant of x over 2, so 2 times secant to the fifth of x over 2 over 5 minus secant cubed of x over 2 over 3 plus c. Alrighty. And that'll be it. Hopefully this is helpful. Okay, I think we got one more ugly one. But this isn't too ugly. It's kind of cute. He's a little baby girl. So, if I were to let u be tangent, then du would be secant squared, but that's over secant to the fifth. And if I let u be secant, then du would be secant tangent, and I only have a tangent squared. Well, let's rewrite this, right? Because tangent squared is sine squared over cosine squared. And 1 over secant is just cosine, so this is cosine to the fifth dx, which will simplify as sine squared, cosine cubed. Whoa, poor notation. Come on now. Come on now. dx. So let's see, I can't do u substitution yet. And if I rewrite my sine squared, then I'll just have cosines involved. So I need to change my cosine cubed. So this becomes sine squared of x times 1 minus sine squared times cosine dx. Right, so then this is the integral of sine squared minus sine to the 4th cosine dx. Because then I can let u be sine of x, and then du would be cosine of x dx. So this becomes the integral of u squared minus u to the 4th du. So u to the 3rd over 3, so sine cubed of x over 3 minus sine to the 5th of x over 5 plus c. All right, that's it. So again, a lot of this is just like rewriting it, right? Because once we made this rewrite, it was a little bit easier to work on it from there. All right, last one. This is something that you guys will not be tested on for the AP test. If it's something that you are, they would definitely give this identity to you. But it's something that you very well could see when you get to college. So I wanted to make sure that you're at least somewhat familiar with it. You can memorize these things with patterns, right? So notice it's sine, sine, cosine, 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 cosine. If it's both sines, then it's a minus. If it's both cosines, then it's a plus. All of these things are the difference of the angle with the sum of the angle. And then notice if they are different functions, it is sine, sine, plus, right? All of them also have 1/2. So you can find the patterns to memorize these things pretty easily. But again, I'll give these things to you if I'm going to test or quiz you on it, and I guarantee you I will at least quiz you on them. So let's use that identity. Since I have cosine, cosine, I'm looking right here. So 1/2 the integral of cosine times the difference, which would be 2 theta, plus cosine times the sum, which would be 8 theta d theta. And then I can just do my antiderivatives. So 1/2 cosine, not cosine, sine 2 theta over 2 plus sine 8 theta over 8 plus c. And that's all you have to do. You can leave it just like that. You can distribute your 1/2 to make that sine of 2 theta over 4 if you want, and sine of 8 theta over 8, but I'm not going to require you to. Okay, that's really all I got for you guys today. As always, please come ask questions and know that I am here for you. And I'll talk to you guys soon. Bye!